The paradox of an infinite universe. Stand at the edge of everything you know and peer into the darkness. What lies beyond? Does the cosmos stretch forever into an endless expanse? Or does it curve back upon itself in ways our minds struggle to comprehend? These are not merely philosophical musings. They are fundamental questions that strike at the very heart of existence itself. The universe is a place of paradoxes. It had a beginning, yet it may have no end. It expands, yet it may be infinite. It contains everything, yet we can only witness a fraction of its totality. To understand the nature of reality, we must confront these contradictions head-on, armed with nothing but mathematics, observation, and the relentless human drive to know what cannot easily be known. 14 billion years ago, everything that exists emerged from an incomprehensibly dense point. Space itself unfurled in all directions, carrying matter and energy outward in a cosmic tide that continues to this day. We call this event the Big Bang, though the name hardly captures its majesty or strangeness. It was not an explosion into pre-existing space, but rather the birth of space itself, along with time, matter, and all the fundamental forces that govern reality. Since that moment, the universe has been expanding. Galaxies rush away from one another, carried on currents of spacetime itself. The farther away a galaxy is from us, the faster it recedes, until at extreme distances, galaxies move away faster than light itself can travel. This is not because they are moving through space at such speeds, but because space itself is stretching, like markings on an inflating balloon. This expansion presents us with a puzzle. If something is expanding, growing larger with each passing moment, then surely it must have edges. A balloon has a surface, a cloud has boundaries. Everything that grows seems to require limits, borders beyond which it does not extend. Yet when we search the cosmos for such boundaries, we find none. Or rather, we find something far stranger. There is an edge to what we can see, but it is not an edge of space. It is an edge of time. Light travels at a fixed speed, approximately 300,000 kilometers per second. Nothing in the universe can exceed this limit. This means that when we look out into space, we are also looking back in time. The light from distant stars and galaxies has taken millions or billions of years to reach our eyes. The farther we look, the deeper into the past we peer. Because the universe had a beginning 14 billion years ago, there is a limit to how far back we can see. Eventually, as we gaze outward, we reach a moment in cosmic history before which there simply was no past. Before this moment, the universe was so dense and hot that matter as we know it could not exist. Light itself could not travel freely, but was trapped in a soup of charged particles. This barrier is called the cosmic microwave background, and it forms the edge of the observable universe. But here is where things become complicated. Because the universe has been expanding during the time that light has been traveling toward us, the objects whose light we see are now much farther away than the distance light has traveled. When we calculate the true current distance to the most remote objects we can observe, we find that the observable universe is not 14 billion light-years in radius, but approximately 45 billion light-years in every direction. This sphere of observability contains roughly 200 billion galaxies. Each galaxy harbors hundreds of billions of stars. Many of those stars are orbited by planets. Some of those planets may cradle life. The sheer number of worlds within our cosmic horizon defies imagination. Yet this vast realm represents only what we can see. The true universe extends beyond this boundary, perhaps far beyond. How much farther does it go? This is where we confront two fundamentally different possibilities, each with profound implications for the nature of reality itself. Either the universe is unimaginably large, but ultimately finite, or it is truly infinite, stretching on forever without end. Consider first the possibility of a finite universe. If the universe contains a limited amount of space, then theoretically, you could fill it with something. Imagine filling it with ice cream, particle by particle. The task would be absurd, requiring more ice cream than could be produced by every star in every galaxy across cosmic epochs. But the amount would be finite. There would be a specific, calculable number of atoms of ice cream required to fill all of space. Yet this concept immediately generates a troubling paradox. A finite universe should have edges. There should be places where space simply stops, where you could reach out and touch a cosmic wall beyond which there is nothing. But if such edges exist, what lies beyond them? The universe, by definition, is everything that exists. How can there be anything outside of everything? The very question seems nonsensical, a linguistic paradox that reveals the limits of human intuition. Does the concept of outside even have meaning in this context? Our brains evolved to navigate three-dimensional space on the surface of a single planet. We instinctively understand edges and boundaries because we encounter them constantly in our daily lives. But the universe operates on scales and principles that defy our evolutionary conditioning. Physics, however, offers an elegant solution to this dilemma. It is possible to have a universe that is finite, yet has no edges at all, no borders, no walls, no outside. To understand how this works, we need to think about the geometry of space itself in ways that challenge our perceptions. Imagine you are an ant, so small that you perceive only a tiny patch of the surface on which you stand. To you, this surface appears flat, extending in all directions as far as your senses can detect. Now suppose this ant begins to walk in what it perceives as a straight line. It walks and walks, never encountering any edge or boundary. Eventually, impossibly, the ant returns to its starting point, having circumnavigated the entire surface. The surface is not infinite. It has a definite, measurable area, yet it has no edges. The ant was walking on the surface of a sphere, perhaps an orange. The two-dimensional surface of a sphere is finite but unbounded. No matter which direction you travel, you will never find an edge, yet you could theoretically map every square centimeter of the surface. The universe might work in a similar way, except instead of a two-dimensional surface curving through three-dimensional space, we would have three-dimensional space curving through a higher dimension we cannot directly perceive or visualize. This geometry is called a hypersphere. Just as the surface of a sphere is a two-dimensional space curved into the third dimension, a hypersphere would be three-dimensional space curved into a fourth spatial dimension. This is utterly impossible for human brains to visualize accurately. We can use mathematics to describe it. We can create analogies and shadows of the concept, but we cannot truly picture it in our minds. Nevertheless, the mathematics is consistent and elegant. In a hyperspherical universe, if you could somehow travel in a perfectly straight line for long enough, you would eventually return to your starting point, having circumnavigated the entire cosmos. From our perspective as inhabitants of this three-dimensional space, we would experience our entire reality as analogous to the skin of the orange, the surface on which the ant walks. We could never step outside it, because there is no outside. The space simply curves back on itself in a dimension we cannot access. But how does space curve in this way? What mechanism could possibly bend the entire fabric of the universe into such an exotic shape? The answer lies in gravity, that most familiar yet most mysterious of forces. Gravity is not a force in the traditional sense, pulling objects toward one another across empty space. Rather, gravity is the curvature of spacetime itself. Mass and energy warp the geometry of the universe, creating curves and valleys in the fabric of existence. Objects moving through this warped spacetime follow curved paths, which we perceive as gravitational attraction. Near a massive object like a star or planet, this curvature is pronounced. Spacetime bends sharply, creating a deep gravitational well. But the effect extends outward, diminishing with distance but never quite reaching zero. Every massive object in the universe contributes to the overall curvature of spacetime, creating a subtle tension throughout the entire cosmic fabric. In principle, If the total mass and energy density of the universe falls within certain ranges, this accumulated curvature could cause space itself to curve back on itself on the largest scales. The universe would close into a hypersphere, finite yet unbounded, with no need for edges or exteriors. If we live in such a hyperspherical universe, how could we detect it? On Earth, we can observe objects disappearing below the horizon, and from this observation, we can calculate the planet's curvature and size. Could we do something similar for the universe itself? Scientists have searched for evidence of cosmic curvature, looking for telltale patterns in the distribution of matter and energy across vast distances. They have examined the cosmic microwave background radiation, that ancient light from the early universe, searching for subtle distortions that might reveal the shape of space. They have measured the geometry of space by analyzing how light travels across billions of light years. So far, these observations have revealed no clear evidence of curvature. Space appears to be flat, or very nearly so, but this does not rule out a hyperspherical universe. It simply means that if the universe is curved, it must be so vast that the curvature is imperceptible from our vantage point. Think again of the ant on the orange. If the orange were enormous, thousands of kilometers in diameter, the ant might explore a vast area and conclude that the surface is perfectly flat, never detecting the subtle curvature beneath its feet. Similarly, if our universe is a hypersphere, it must be so large that even our observations across 45 billion light-years fail to detect the curve. The mathematics suggests that for the universe to appear as flat as observations indicate, a hyperspherical universe would need to be at least 1,000 times larger than the observable portion. It could be 1,000,000 times larger, 1,000,000,000,000 times larger, or more. There is no upper limit to how large it might be, only a lower bound on its size. Some physicists have proposed even stranger geometries. Instead of a hypersphere, the universe might resemble something more like the surface of a donut, a shape mathematicians call a torus. Extend this concept into higher dimensions, and you get a hypertorus, or hyperdonut, an exotic shape as impossible to visualize as the hypersphere, but with different properties. In a hyperdonut universe, space would still be finite and unbounded. Travel far enough in any direction, and you would return to your starting point. But unlike a hypersphere, a hyperdonut has a more complex geometry. The distance around the universe would not be the same in all directions. You might circumnavigate the cosmos in 10 billion light-years traveling one way, but require 50 billion light-years traveling in a different direction. This asymmetry would create bizarre observable effects. Light from distant galaxies might reach us from multiple directions, having traveled different paths through the twisted topology of space. We might see the same galaxy in two different places in the sky, appearing at different stages of its evolution, because the light took different amounts of time to reach us along different routes. Imagine looking through a telescope and seeing a young star forming in one part of the sky. Then you turn your telescope to the opposite side of the sky and see that same star, now ancient and dying, because the light has traveled a much longer path to reach you. The universe would become a cosmic hall of mirrors, where the same objects appear multiple times, frozen at different moments in their histories. The geometry of a hyperdonut is so unusual that such a universe could, in principle, be quite small by cosmic standards. It might be only a few times larger than the observable universe, making it the smallest possible closed universe. Yet it too could be vastly larger. Without clear observational evidence, we cannot determine which geometry, if any, describes our universe. These finite models are intellectually satisfying in some ways. They avoid the conceptual difficulties of infinity. They provide a universe with a definite size, even if that size is incomprehensibly large. Yet they are not the only options, and indeed, they may not even be the most likely scenario. What if the universe is not merely large, but truly infinite? What if space extends forever in all directions, with no boundaries or curvature bringing it back on itself? This possibility is both the simplest and the most mind-bending. In fact, The standard cosmological model that most scientists use to describe the universe predicts exactly this: an infinite universe. This model, built on Einstein's general relativity and refined through decades of observations, describes a universe that is flat on large scales and extends infinitely in all directions. While scientists often use this model primarily to make calculations about the observable universe, if taken at face value, it describes a cosmos that goes on forever. An infinite universe is, in some ways, harder to conceptualize than a hypersphere. At least with a hypersphere, we can imagine an ant on an orange and extrapolate upward. But true infinity defies analogy. There is no edge anywhere. No matter how far you travel, there is always more space ahead of you, more galaxies, more stars, more planets, more of everything, continuing forever in every direction. This infinite expanse raises immediate questions that strain our understanding. If the universe is infinite now, was it always infinite? Did it exist forever into the past, or did it have a beginning? And if it had a beginning, how can something that already extended infinitely become even larger through cosmic expansion? We have substantial evidence that the universe had a beginning. The Big Bang is not merely a theory, but a framework supported by multiple independent lines of evidence. We observe the expansion of space. We detect the cosmic microwave background radiation, the afterglow of the early universe. We measure the abundances of light elements formed in the first minutes after the Big Bang. All of this points to a universe that emerged from an extremely hot, dense state approximately 14 billion years ago. Yet how can something infinite have a beginning? This seems paradoxical. If the universe was infinite a second after the Big Bang, it must have been infinite at the moment of the Big Bang itself. You cannot go from finite to infinite by any process of growth or expansion. Either something is infinite or it is not. One way to resolve this is to recognize that the Big Bang was not an explosion from a single point into pre-existing empty space. Rather, it was the beginning of space itself. An infinite universe could have emerged in its entirety at the moment of the Big Bang, already infinite from the very start, but with all points initially very close together. As space expands, the distances between points grow, but the universe remains infinite at every moment. This brings us to another puzzle. How can something infinite expand? If space already extends infinitely in all directions, what does it mean for it to grow larger? The resolution lies in understanding what cosmic expansion really means. It is not that galaxies are flying apart through space, like fragments from an explosion. Rather, space itself is stretching. The distance between any two galaxies increases over time, not because they are moving through space, but because the space between them is growing. Even an infinite space can exhibit this property. At any given moment, if you measure the distance between two galaxies, you will get a certain number. Wait 1 billion years, and the distance will be greater, because space has stretched. This is true everywhere throughout an infinite universe. Infinity can grow larger, in the sense that distances increase, even though the universe remains infinite in extent. Welcome to the paradoxes of infinity. Our mathematical understanding allows us to work with these concepts precisely, but our intuition rebels against them. We are finite beings, living finite lives, unable to truly grasp the infinite except through abstract reasoning. But infinity becomes stranger still when we consider what it might contain. As you travel through an infinite universe, you encounter an endless variety of galaxies, stars, and planets. New wonders reveal themselves at every turn. Cosmic structures of breathtaking beauty and violence, perhaps civilizations beyond counting, living out their dramas on countless worlds. Life in forms we have never imagined, adapted to environments we cannot fathom. Yet after traveling unimaginable distances, farther than the mind can conceive, you might encounter the most unexpected thing of all, yourself. An exact duplicate of you, living an exact duplicate of your life, watching this exact video at this exact moment. How can this be? the reasoning is both simple and profound. Everything that exists, from the smallest subatomic particle to the largest galactic supercluster, is made from a finite set of fundamental building blocks. Quarks, electrons, photons, and a handful of other particles governed by a fixed set of physical laws. These particles can combine in an enormous number of ways, but that number, however large, is still finite. Consider a deck of cards. There are only 52 cards, yet they can be shuffled into approximately 80 unvigintillion different orders. That is 8, followed by 67 zeros, a number so large that if you shuffled a deck every second since the Big Bang, you would not have explored even a tiny fraction of the possible arrangements. Yet the number is finite. Given infinite shuffles, eventually you would repeat an arrangement. Similarly, the particles that make up everything in the observable universe can be arranged in a truly astronomical number of ways. The number is so large that it makes the shuffled deck seem trivial by comparison. Yet it is still finite. In an infinite universe, with infinite space filled with infinite matter, these arrangements must eventually repeat. This means that somewhere out there, unimaginably far away, there is a planet identical to Earth. On that planet is a person identical to you in every detail, down to the last atom, living a life identical to yours, having identical thoughts at identical moments. There may be infinitely many such duplicates, scattered throughout an infinite cosmos. The distance to the nearest such duplicate is almost certainly beyond comprehension. Calculations suggest that to find another Earth identical to ours in every detail, you would need to travel approximately 10 to the power of 10 to the power of 29 times the size of the observable universe. To write this number in full would require more digits than there are particles in the observable universe. It is a distance so vast that, forever far away, is a reasonable approximation. But in a truly infinite universe, even this incomprehensible distance is just a finite journey. Travel far enough, and you will find not just one duplicate Earth, but infinitely many. And not just Earths identical to ours at this moment, but Earths at every possible stage of their history, and Earths where history took different turns at every possible decision point. There would be Earths where dinosaurs never went extinct, Earths where humans never evolved, Earths where you made different choices at every juncture of your life. The infinite universe would contain every possible variation on every possible theme, played out across infinite worlds. Yet we must pause here. While these scenarios are mathematically possible, we have entered the realm of speculation rather than science. Just because something is possible does not mean it must occur. Perhaps the universe, though infinite, is more homogeneous than these arguments suggest. Perhaps the laws of physics prohibit such exact duplications. Perhaps probability works differently on cosmic scales than we imagine. More fundamentally, none of these ideas about infinite duplicates can be tested or proven. If the nearest duplicate Earth is impossibly far away, we can never observe it or interact with it in any way. It exists, if it exists at all, beyond the boundaries of causality itself, forever isolated from us by the expansion of space and the finite speed of light. This is the frustrating truth about questions of cosmic infinity. We may never know the answer. If the universe is truly infinite, we cannot observe its infinity. We can only observe our finite bubble, the observable universe. Everything beyond that horizon is, in principle, forever beyond our reach. Even this observable universe is receding from us. As space expands, distant galaxies accelerate away. Galaxies that we can see today will, in the far future, cross a threshold beyond which their light can never reach us. The observable universe is slowly evaporating, becoming smaller over cosmic time as galaxies slip beyond the cosmic horizon one by one. In the unimaginably distant future, the only galaxies visible from Earth will be those in our local group, gravitationally bound together and thus not pulled apart by cosmic expansion. The rest of the universe will have receded beyond observation. Future civilizations, if any exist, might look out at the cosmos and see only darkness beyond their local cluster, unaware of the vast universe that once was visible. For us, trapped in our particular moment in cosmic history, the universe is effectively finite. We can see only so far. We can interact only with matter and energy within our cosmic horizon. Everything we call the universe, everything we can measure, observe, or theoretically visit, is contained within a sphere 45 billion light-years in radius. This may feel limiting, but consider what this finite realm contains. 200 billion galaxies, hundreds of billions of trillions of stars, planets beyond counting, cosmic phenomena of unimaginable diversity and grandeur. Black holes, neutron stars, supernovae, nebulae, pulsars, and structures we have barely begun to catalog. And perhaps, somewhere in that vastness, other minds looking up at their skies and asking the same questions we ask. This finite universe is more than sufficient for every dream, every ambition, every exploration that humanity and its descendants could conceive across billions of years. We will never exhaust its mysteries. We will never catalog all its wonders. Even this limited slice of cosmic totality is, in practical terms, infinite in its richness and complexity. Perhaps that is the most profound realization of all. Whether the universe is truly infinite or merely incomprehensibly large is, in some sense, irrelevant to the human experience. Either way, we are embedded in something far grander than we can fully grasp, surrounded by mysteries that will occupy our curiosity for as long as consciousness persists. The question of cosmic infinity may never be answered definitively. But the quest to answer it, the tools we develop, the observations we make, the theories we construct, these endeavors expand our understanding and reveal truths we never anticipated. Every question answered opens new questions. Every horizon reached reveals new horizons beyond. We stand at the edge of knowledge, peering into darkness, driven by an insatiable need to know. And whether the universe is finite or infinite, that drive itself is perhaps the most remarkable thing in all of creation. That matter can organize itself into patterns complex enough to contemplate its own origins, to question the nature of existence itself, is a wonder beyond measure. The universe may or may not be infinite, but our capacity for wonder, our relentless curiosity, our determination to understand, these qualities make us infinite in spirit, if not in substance. And in a cosmos that may extend forever or may curve back on itself, that may be the most important infinity of all. Let's plunge deeper into the paradox of infinity and the marvels of cosmic geometry, widening our lens beyond the wall of our known universe and stretching imagination as far as science allows. If you were to journey through a hyperdonut universe, one shaped not like the skin of an orange, but like that of a cosmic donut, you would encounter peculiar distortions of distance and time. Imagine two explorers launching in opposite directions. One returns to their starting point much sooner than the other. The path through one part of space bends more tightly than elsewhere, and light from remote galaxies could take vastly different routes, arriving at your telescope from multiple directions, a genuine cosmic hall of mirrors. Stare at a distant star's birth in one quadrant, then witness its demise in another. Not only do you see faraway things mirrored, but you see them in different epochs because their light traveled a longer way round in one direction. This strange topology hints that the universe could be much smaller, potentially only a handful of times larger than the observable sphere, yet still lacking a border, just warped in surprising ways. We do not know how large a hyperdonut could be, only that its pangs of cosmic geometry could twist our observations into odd symmetries. But what if we look beyond all geometric oddities, beyond hyperspheres, hyperdonuts, and all finite realms? What if reality itself is infinite, stretching without boundary forever? Cosmology's most accepted model, the one undergirded by decades of telescope data, and the crowning equations of general relativity, leans toward infinity. Most calculations operate within the safety of our observable universe, but when taken literally, these equations propose a universe that's infinite, no border, no edge, just more galaxies in every direction. Infinity is impossible to visualize, a concept that resists the limits of not only our sight, but our very imagination. Within this infinite domain, subtle paradoxes arise. Did infinity always exist? Or was there a time when not even empty space stretched across reality? The evidence for the Big Bang suggests there was a definite beginning. Our universe appears to have emerged from an initial, unbelievably dense state, a time when all matter and energy were pressed together into a cosmic singularity, then expanded into what we perceive. But if the universe began, how can infinite space spring forth from a beginning? How does something infinite grow even larger as expansion continues? The answer lies within the peculiar definitions of cosmic expansion. It's not matter moving outward, but space itself stretching. Even in infinity, all distances between galaxies grow over time. Travel through such a universe, and you'd never run out of new discoveries. Each direction offers further wonders, more stars, more planets, more life, possibly even alternate forms of intelligence. The most shocking implication, however, occurs in the framework of quantum probability and mathematical repetition. Eventually, you'd encounter yourself. Not metaphorically or spiritually, but literally a perfect duplicate of you, constructed by a rearrangement of particles in a distant corner of the cosmos. Why? Because everything in the universe is made of a limited set of building blocks. There is a finite number of subatomic particles, governed by a finite set of physical laws. These constituents can assemble in vast, yet ultimately finite number of combinations. You could shuffle a deck of cards in unthinkable ways, but after enough shuffles, repeats become inevitable. If there are finite options for how matter is structured, but infinite space for it to occur, then at some point, perhaps impossibly far away, every arrangement, every planet, every living being must repeat. There will be another Earth, another you, watching another science documentary at the same time. The scale required for this duplication is monumental. To encounter a truly identical Earth, you'd have to travel a distance so vast it dwarfs the entire observable universe so large. The notation itself stretches the capabilities of language and mathematics. And yet, in a true infinity, the absurdly improbable becomes not only possible, but inevitable. Perhaps, in other realms of this infinite cosmos, there are variations worlds where evolutionary history took a different turn. Earths with no humans, or with drastically different forms of life. Or perhaps even slight changes in your own life. Moments where choices diverge and fate follows new pathways. The infinite universe becomes a tapestry of every possibility, every alternate future and past, woven into the fabric of reality. Yet this is speculation, not testable science. It is grounded in mathematics and physics, but beyond the reach of observation. While the repetition of particle arrangements is plausible, the probability may be so vanishingly small that any exact duplicate lies forever out of reach. Here is the catch. Even if the universe is infinite, we cannot access its fullness. The observable universe, the bubble of space-time we inhabit, is bounded by the speed of light and the age of the cosmos. Everything we know, every star we see, exists within this finite realm. As time progresses and the universe continues to expand, the most distant galaxies will drift away, receding beyond the reach of telescopes and instruments. In the far future, perhaps countless billions of years hence, only the galaxies gravitationally bound to ours will remain visible. All others will have vanished into the darkness beyond the cosmic horizon, effectively leaving us alone in an island universe. For humanity, bounded by time and caught in the drift of cosmic expansion, the universe feels finite. The visible domain, a radius of 45 billion light-years, contains all we can interact with, all we can measure, all we can ever explore. Its richness is more than enough for every scientific ambition, every journey, every quest. Within this sphere are more than 200 billion galaxies, hundreds of billions of stars in each, planets by the trillions, endless phenomena, some so strange they await discovery. This bounty is enough to challenge our curiosity for eons to provide meaning, purpose, and exploration long after Earth's own sun grows cold. The pursuit of knowledge and understanding is itself the gift the universe bestows. Whether the cosmos is finite or infinite, committed curiosity transforms isolation into possibility and brings clarity to mystery. And though the larger questions may elude final answers, whether reality extends forever, repeats itself, or folds back upon its own dimensions, the journey of inquiry is what matters most. Each experiment, each observation, each mathematical breakthrough brings new light to the darkness. Infinity is not merely a matter of numbers, nor an abstract concept reserved for theorists. It is the grand stage upon which existence unfolds. Whether its scale is realized in physical fact or simply in the staggering sweep of our imagination, it gives context and wonder to every starlit night, every atom, every human thought. Let us persist in curiosity. Let us marvel at the paradoxes, confront the unknown, and build ever grander stories of the universe. For in the quest to understand the infinite, we unlock potential that exceeds the boundaries of reality itself. This is the paradox of the infinite universe, and it is the birthright of all who look upward, who ask not just what is, but what might be, who make wonder their companion through the cosmic dark.